Good morning, class. In this lecture, we'll discuss automata and particularly the finite automata. Till now, we have discussed the basics of the subject, that is, what is computer, what is computing, what is theory of computation, what is the importance of this subject, and so on. In the previous lecture, we also have discussed the basics of the automaton, that is the basic computer or the abstract computer or abstract computer machine is also known as automaton or automata. There are different types of automata available, and the very first automata or the type of automata which is finite automata. We have another type of automata which is push down automata. Fine. So finite automata is nothing but a kind of automata or a type of automata. So in this lecture we'll discuss finite automata. Let's move to the next slide. So finite automata can be categorized into two categories. So this is the first category, finite automata without output, and this is the second category, finite automata with output. So we have two types of finite automata without output and finite automata with output. Fine. So finite automata with output can be divided into three categories. The first one is deterministic finite automata, which is also known as DFA. The second is non-deterministic finite automata, also written as NFA. And the third one is epsilon NFA, epsilon non-deterministic finite automata. So I am repeating, finite automata is of two types. The first is finite automata without output, and the second is finite automata with output. Fine. So the finite automata without output is divided into three categories. The first is deterministic finite automata, which is DFA, deterministic finite automata. The second is non-deterministic finite automata. This is the second category or second type of finite automata. And the third is epsilon NFA, epsilon non-deterministic finite automata. Okay, so hope this is clear to you. In the second classification or the second category, that is finite automata with output, we have two types of machines. First is called as Moore machine and the second is called as Mealy machine. Moore machine and Mealy machine. These two automata or these two machines produce some output, whereas these three machines or these three automatas do not produce any output. So these are without output, and these are the machines which produce some output. We will see or we will discuss all these five types of finite automata one by one in the coming lectures. Fine. So I am repeating, we will discuss these five, 1, 2, 3, 4 and 5. So these five types of finite automata in coming lectures one by one. Okay. In this lecture we will start with deterministic finite automata, that is DFA. So what is automaton? What is automata? This is already discussed in the previous lecture. So go through to that lecture first, then come to this lecture. Deterministic finite automata or such basic abstract machines can be written, can be represented or can be explained in two different ways. The first way of explanation or first way of representation is the mathematical model or the mathematical way to represent them or to write them. And the second is you can describe or you can represent these automatons with the help of a state transition diagram. I am repeating, you can represent the automata either by using a mathematical representation, which is written here, and the second is state transition diagram. So we already have seen one example of the state transition diagram of an automaton in the previous lecture, which was the ticket vending machine. Fine. And the diagram was similar to this diagram. So this is state transition diagram. One can represent the automata by using state transition diagram. This is one way of the representation, or one can use the mathematical way to represent the same automata. Both are the same. Fine. So let's understand what this representation is all about. According to this, an automaton whose name is M is a 5 tuple set. So 5 tuple set means a mathematical set 1, 2, 3, 4, 5. So these are the 5 tuples. So M is, or the automaton is, a 5 tuple sets Q, sigma, Q, small q, F and delta. Fine. So where Q is, that is the first set, is a non-empty set of states. Fine. So every automaton will have some states. Fine. uh, some states like these are. So these are the states of the automaton which are in the circle. So Q is non-empty set of states. Fine. Whereas the sigma is the input alphabet, or this is a set of characters which will be taken by the machine as an input. I am repeating, the sigma is called as input alphabet. The meaning of this input alphabet is, this is the set of characters or set of alphabets which are taken as input by the machine. So every automaton will have an initial state which is represented by Q. This is the initial state. So machine will have only one initial state. Machine cannot have multiple initial states. It will have only one initial state. Whereas this capital F is a non-empty set of final states. A machine may have more than one final state. So it should have at least one final state, but machine may have more than one final states. Next and the last, the machine can remember some properties of its input by being in a particular state, or by through a state transitions. So for that there is a transition function, how the machine is moving or having transaction from one state to the another state, and that is mathematically defined by a function which is sigma, and that is Q cross this sigma arrow Q. What is the meaning of this? We will discuss it in the next slide. But this is a transition function which is representing the transitions of a automata from one state to the another state. Fine. Please excuse me for a minute. Okay. Now let's move to next slide. So if it is not clear till now, it will be cleared in this example. Let's take it by one example. Suppose we are given the state transition diagram of the automata. Fine. Then you have to represent it in the mathematical way by using 5 tuple sets. Okay, so this was the slide taken from the previous slide. So M is a 5 tuple set Q, sigma, small q, F and delta. Okay, now look at this. Q is non-empty set of states. So how many states are here? Q0, Q1, Q2, Q3 and Q4. 5 states are here. So Q is a set of these states, Q0, Q1, Q2, Q3 and Q4. So you will have all states here, which are the states of this state transition diagram. So this sigma is the input alphabet, that is set of characters which are taken as input by the machine. So machine is taking either small a or small b as an input. Fine. So either small a or small b. There is no small c, no small d. So only two characters are taken as input. That's why sigma is the set of these two characters or these two alphabets. So this is called as input alphabet. Q is the initial state. So which one is the initial state here? So this is the initial state which is pointed by this arrow, starting arrow. So this is marked as initial state. So machine will have only one initial state. So Q is Q0, that's why here. And remember, this initial state should be any state from the Q, that is the Q is subset of this capital Q. So if there are Q0, Q1, Q2, Q3 and Q4, you cannot have Q5 here. Remember, you cannot have Q5 or Q6 here. So any state which is the part of this capital Q can be the initial state. Okay, so out of these 5 states, Q3 and Q4 are final states. Why? Because they are marked by double circles. So if there are double circles, they are final states. So that's why capital F is pointing to Q3 and Q4. These two are the final states. Now coming to the last part of the automaton, which is the transition function, and this transition function is written as Q cross, this is the cross product. Hope it is clear to you from the basic mathematics what is cross product. Q cross sigma arrow the Q, any state from the Q. So let's find out the cross product. So Q, these 5 states Q0, Q1, Q2, Q3 and Q4 cross and the sigma, which is small a and small b. The cross product of these two will have these pairs Q0 comma a, Q0 comma b. This is the result of the cross product of these two. Q1a, similarly Q1b, Q2a, Q2b. Q3 is not written here, but it should have the Q3 here. Fine. So Q3A, Q3B, and finally Q4A and Q4B. I am repeating, Q3 pairs are not written here, but they should be here. Fine. So the pair Q0A is having transition to Q1. So look at this diagram. Q0, the current state is Q0 and input taken is small a. The meaning of this pair is the current state is Q0 and the input is small a. Now look at this. The state is Q0 and the input is A. Then the transition is to Q1. Okay, I am repeating this line. If the machine is in state Q0 and the machine is taking the input small a, then the machine will have a transition from Q0 to Q1. That's why the Q1 is here. So these are the states after transitions. So these are, which is to the right hand side of this arrow. So these are the states after transition. Okay, and these are the states which is the current state, and this is the input taken or the input consumed. So if look at this one, this pair, fine. So if current state is Q1 and the input is A, so current state is Q1 and the input is A, so machine will have a transition to the new state which is Q3. So Q1 on input A will have a transition to the state Q3. Hope these transitions are clear to you. Okay. How many transitions will you have? It depends on the number of states and the number of input characters. So the cross product of these two will have around 1, 2, 3, 4, 5, 5 into 2, 10. So I think these are the 10 pairs. Fine. Fine. So this is the mathematical representation of an automaton, which is given as an example here. So look at this transition. Look at this transition. The current state is Q2 and the input is A. So the machine is moving nothing. There is a self transition from Q2 to Q2. This also is possible. Fine. Okay. So hope this part is clear to you, the transition function. So this is the cross product, and the cross product will map to some state of the this automaton. Now let us look at another example. In this example, the state transition diagram is given to you, and you have to represent this automaton in a mathematical way. Fine. So mathematical representation you have to write for it. So as we all know that automaton is a 5-tuple set, in which the first set is the capital Q, which is set of states. So here it is clear that we have 3 states, Q1, Q2 and Q3. That's why Q1, Q2 and Q3. The sigma is the input alphabet. The machine is taking 2 characters, either 0 or 1. That's why 0 or 1 here. So Q means the starting state or the initial state is Q1 here. So it is written in the descriptive way, sentence wise. Otherwise you can write Q equal to Q1. So this is our initial state. How it is identified? That you will have a starting arrow here, which is coming from no state. That's why this is the initial state. And F is set of final states. So how many final states do we have here? Only one final state. How to identify the final state? The final state will have double circles, double concentric circles. Okay, that's why only one state here. So till now we have explained 4 components: the set of states, the input alphabet, the initial state and the final state. Now what is left? The transition function, which is delta. Now you can give transition functions in two different ways. There are two methods to write this transition function. One is this one, which is written here. This is called as transition table, and the second is which we already know in the from the previous lecture. Fine. So both are same. You can use either transition table or you can use this method. Fine. So we already know that this method, but look at this one. These are the input alphabets and these are the states, current states. So this is current state q1 and this is the input alphabet 0. So q1 on taking input 0 will have a transition to state q1. Repeating, q1 on taking input 0 will move to state q1. Okay, look at this. q1 on taking input 0 is moving to the state q1. That is a self transition. Look at the second transition, that is this one. q1 on taking input 1 is moving to the state q2. That is the second one. q1 on taking input 1 is moving to q2. So these states are the states after transition and these are the current states. Now look at this example. q2, if current state is q2 and input is 0, then it will move to the q3. q2 on 0 is moving to q3. So this is transition table, one method to represent the transition function, and this is second method, we already know it. So q1 comma 0, this is the current state, input is 0 and state after transition. So both are equivalent. You can use any method to represent the transition function. Hope it is clear to you. Fine. So this is the mathematical way to represent an automaton. Now coming to the question, why it is called as finite automaton? Fine. So this is called as finite automata because we have finite number of states. So these states will be finite. You cannot have infinite states here. Fine. So that's why it is called as finite automaton. Hope this is clear to you. Why it is called finite automaton? Because we have finite number of states here. Okay. Now coming to the second part or the second question, why it is called as deterministic finite automaton? What is determinism here? Deterministic. Why it is deterministic? Okay. Now look at this transition function. Look at this transition function. So the meaning of this transition function is, this is the function which is making it deterministic. And what is the meaning of it? The meaning of it is for every state and every input, I'm repeating, for every state and each input, there is exactly one state after transition. Look at this case. q1, then we have q2, then we have q3, and for every state we have two inputs, possible input, either 0 or 1. That's why two combination. q1 either 0 or 1, q2 either 0 or 1, similarly q3 either 0 or 1. So for every combination or every pair, there is exactly one state. Okay. So if any pair is missing or any transition is missing, then this is not deterministic finite automata. This could be non-deterministic finite automata. Okay. If for every pair, suppose all pairs are present, but for a particular pair there are two states after transition. Listen this statement carefully. For suppose a particular pair is missing, which is not given here or not given here in the diagram also. So straightforward, this is not deterministic finite automata. This could be non-deterministic finite automata. This is NFA. Okay. Now the second point, suppose all pairs are given. Okay, but for a particular pair there are two states, suppose q1 and q2 also, so two states after transition, then also this is not deterministic finite automata. This could be non-deterministic finite automata, but it is not deterministic finite automata. So this is the basic difference between DFA and NFA. So what should be in DFA? First, for every state and each input, there should be all pairs. So 3 into 2 equal to 6. We must have 6 pairs here. 1, 2, 3, 4, 5, 6. So 3 states into 2 input alphabet. That's why 6 pairs. Then for each pair, there should be exactly one state after transition. This could be the same state, that is Q1 and Q1. It's okay, there is no problem. Q1 and Q2, no problem, but there should be exactly one states. If there are two states, Q1 and Q2, then this is not deterministic finite automata. Okay, hope this point is clear to you. Second, so you can represent the transitions either in this way, or you can represent the transitions by using transition table. There is no difference between these two methods. You can use either this method or you can use this method to represent the transitions. Hope it is clear to you. Fine. Now this is the assignment question to you. What you have to do, you have to represent this deterministic finite automata by using mathematical representations. So how many states are given here? We have two states. The name of the first state is QE and the second of the next state is QO, or you can write Q0. What is input alphabet? So you have two characters in the input alphabet, 0 and 1. Which one is the initial state? So this is the initial state. How many final states? Only one final state. This is the final states. Okay, now coming to the transition functions. So create a transition table or write it in a pair way. So it's up to you. Note it down. This lecture we will discuss rest of the part in the next lecture.